Welcome to Lesson 7E, Temperature Inversion, Reflecting Ground, Part 1. We're going to do the exact same three cases that we did before, except now it's going to be for a reflecting ground. So we're talking about Gaussian plume with temperature inversions and a reflecting ground. So case 1 is a ground-based temperature inversion with the stack above the top of the inversion. So this is the same case 1 we had before. The only thing difference is now we have a reflecting ground. So the plume is going to hit and then reflect above the temperature inversion. This is unstable, and below the temperature inversion, or in the temperature inversion here, it's stable, which we always color blue. So this is the inversion, and in this case we have H, this combined stack height, the stack plus the buoyancy, H is greater than HT. So for this case we have the plume up above the top of the ground-based temperature inversion. HT is the top of this temperature inversion, and the plume therefore hits that temperature inversion. It cannot penetrate because it's like a lid, like we've talked about several times. So the plume theoretically will never hit the ground. We call this a lofting plume because it lofts up and it's flat on the bottom. And it turns out that there's no need to calculate anything because this plume never hits the ground. So this is a trivial case like it was before with the absorbing case. There's no hazardous area on the ground, so this is the trivial case where if I ask you what's the hazardous area, you would say there is none. We never have a problem. So this is a good situation as far as air pollution is concerned. People breathing here never see that, never smell that, never breathe that air pollution no matter how far downstream you go. Okay, so that's a trivial case. Case 2 is the case with the ground-based temperature inversion, again, with the source now below the top of the inversion. So again, HT is to the top of the inversion. So this is the inversion here. Remember, the temperature is increasing in temperature inversion. So it's unstable up here. And again, it's stable in here, and this time H is less than HT, the same case 2 that we had previously. The only difference now is that this is now a reflecting instead of an absorbing ground. So how do we deal with this? Well, we have to do what we did previously and make an image source under the ground here to make this a reflecting ground, but we've already done that. So this is now what we call a fanning plume because the plume is entirely within the temperature inversion. We already have a Gaussian model with a reflecting ground. We've talked about that before. We added this image source and we came up with the equations. We really can use that with no modification other than we use stability classification F, as I say here, because that's the most stable of all the Martin model stability classes. So this is a fanning plume that spreads slowly vertically, it spreads fast horizontally, but eventually it will hit the ground and then we'll be able to calculate a hazardous area. This is just the same model. You already have this programmed in your Excel or your MATLAB or whatever you're using, so it's just a matter of running that. And the only thing you have to change is the class, change it to F, and we already have the equations for that. So the equations are all identical. So let's do an example. Gaussian plume, ground-based temperature inversion, reflecting ground. This is the problem I've copied and pasted it, I don't know how many times now. We've seen this over and over again, this same nasty chemical plant. And this time there's a ground-based temperature inversion. So like we're talking about with H less than HT. So we don't have to do anything different other than realize this is a reflecting ground. So make sure we use the right equations. In fact, it's the exact same example as lesson 7C. If you look back at that one, except here we have a reflecting ground, whereas in 7C we had an absorbing ground. Same numbers, everything's the same here. Our HS is the same, our delta H is the same, and therefore we can calculate H here is 100 meters, just like we had before. This is our U, same as that lesson 7C example. Remember, I had to lower U because you don't really get these ground-based temperature inversions unless the speed of the wind is less than about 3 meters per second. So I set it at 2.85 here just as an example. Have the same m.js, and this one has the ground-based temperature inversion up to 205 meters, so we can verify that H is less than HT. since h is 100 meters. The ground reflects. So here I copied and pasted and changed that word from absorbs to reflects, and I added this. It does not absorb. PEL is the same as before, so this is all identical to the previous problem. I want to do two things here. I want to plot mass concentration as a function of x at ground level. So when you see at ground level, that means at z equals 0. I could just as easily do this at other z's, as you have had to do in some quizzes and homeworks, directly downwind. So that means at y equals 0 along the center line of the plume. And I could, again, easily pick a different y. And then I want to also plot the hazardous area, again, at ground level, z equals 0, downwind of the stack. All right, so let's solve this. Let's use the Gaussian+plume equation for a reflecting ground. So I looked back at one of the old lessons and got this equation, or also on the equation sheet. And the only thing we have to be careful, since we're inside the temperature inversion, the plume is entirely in temperature inversion. We use class F, so make sure you have the proper coefficients there. The first thing I did was I did some algebra for you. I used this mathematical identity that we've been using many, many times and made this equation into this equation. So I just separated the y out by itself so that we can do part B, calculate this hazardous area easily. So how do we solve this problem? Well, we've done this many times already, so I'll just kind of summarize here. For part A, all we do is solve this equation. I'll call this equation 1. So for part A, all we have to do is solve this equation 1 directly at the center line, y equals 0, at ground level, z equals 0, and you just pick various x values and plot Cj versus x, and then we'll compare that to the PEL. And then for part B, we want to plot the hazardous area at ground level again, so we'll set z equals 0, and that involves solving equation 1 for y. For part B, all we do is set Cj equal PEL, solve 1 for y, and we do that at z equals 0, or we can do it for any other z and some range of x. And you should get this equation. If you look back in your notes, you should have already done this back in a previous lesson, lesson 7c, because this is exactly the same equation that we had in lesson 7c. I just rewrote it with these all combined for you. So it's actually quite easy. Go from here to here. You've done it several times already. The only difference between then and now is this class F that we're now using. I did it in Excel and I changed my A, B, C, D, etc. coefficients to class F. And then I plotted, doing this exactly the way I did before. And I'm also comparing the old case, the absorbing ground case from previously. So this was 07C. And this one is now, which is lesson 07E. And remember before we had this very small hazardous area, it just barely peaked above the PEL. This is the PEL here. So we barely got above 50 just for a small range of x's. Now we have this red one, which is the reflecting case, reflecting ground, and this one was the absorbing ground. So you see that we have a much bigger, it's actually a factor of 2 since it's on the ground. So the actual Cj goes up by a factor of 2 at any x since it's right on the ground level, as we talked about previously. But the hazardous area, or the hazardous line in this case, goes a lot bigger. Even though it's a factor of 2 in Cj, it's much bigger than that as far as the hazardous area. So that's part A. And then for part B, I plotted the hazardous area. And again, I compared the plane absorbing ground case, and I compared that to the reflecting ground case. I put these right on top of each other at the same x locations. So our hazardous region for the absorbing case was very small, whereas our egg here, I like to call these eggs, we have a huge egg for the reflecting ground case compared to the absorbing ground case. And I mentioned this previously, I think, but I may have not have actually written it down. So I'll take this time to make sure you know what we're plotting here. By now you should, but this line is where Cj is equal to PEL. Inside the egg, Cj is greater than PEL, and outside the egg, Cj is less than PEL. So that's why we call it the hazardous area. So everything inside here is the hazardous area. And so this is really all there is to it. You'll have a quiz, but life is getting easier for you because you can use exactly the same software that you did previously. You just have some different numbers. And remember, when the plume is inside the temperature inversion, you always use class F. I want everyone to get 100 on this quiz. There's no reason not to. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.